I'm Anton, and my talk is about best tools and practices we learned over the years scaling our Erlang system. So it's been 4 years since our last talk here at this conference, and we've grown quite a bit since then. So we tripled our users. We now have 1.5 billion monthly active users and over 1 billion daily active users. And our systems, other subsystems, have grown quite a bit as well. Look at this videos. Not only we were able to keep up with the growth and add quite a bit of new features along the way, we also managed to make a better and more reliable system. And to a large extent, it was possible because of our use of Erlang. So what kind of system our Erlang part is? At its core, it does reliable delivery of messages between clients and does it as fast as possible. We also strive for keeping a highly available service. And if you look at just this list, it may seem like a more traditional telecom system, but the way we're different is we have to handle peak load at a global scale. If we are overloaded, it means our users can't connect and can't send messages. This is a high-level diagram of what our architecture looks like, and it hasn't. The Erlang part of it hasn't really changed in probably 5 or 6 years. So we've been running like that for a while. This gray rectangle over here represents a large geographically distributed Erlang cluster, and the green rectangles inside of it are Erlang nodes. Our clients connect over TCP to one of front-end nodes. Most of our clients are mobile clients, so this is the largest kind of tier. And the TCP connection and the session stays open while the client is active. On the other end of this connection is a Erlang process. We spawn it on when connection is initiated, and it exits on disconnect. This process maintains a session. When it starts, it constructs that session by querying multiple backends. For example, we need to authenticate the client. We need to check whether it's blocked or not. We need to see if we have any messages or notifications to deliver to it. If two clients are online, meaning connected to a front end, once they find each other, they can send the message flow from when they exchange messages. The protocols go directly between the chat nodes, so all the chat nodes are interconnected. We also have more than 40 different type of backend clusters. Individual backends handle usually small portion of system or product functionality and sufficiently decoupled from each other. Some of them do talk to each other, though. And so this is the first level of isolation that helps us keep the system reliable. So one of backend, for example, can go completely down, which doesn't happen often at all. And depending on what type of backend it is, the rest of the system may be still running fine or in degraded mode. And chat nodes here are can go down at any time. and clients will reconnect to another one. A couple of examples of non-Erlang systems that we run. One is voice and video traffic proxying, and another one media uploads, downloads. And even in those cases, all the signaling goes through the main chat channel and handled in Erlang. Any questions about that? All right, let's move on. So databases. So the reason why I chose to talk about databases is I think we approach them in a unique way, and that has worked really well for us. So what you notice on this diagram representing the Erlang part of our system is there are no databases. And the reason is because we run them embedded in backend nodes. They literally run alongside the application code in the same Erlang VM. And half of our backend clusters are stateful, which means they run some sort of databases. If you compare this setup to a more traditional one where you have separate remote databases, this is a lot simpler. In a remote database case, you will have to solve connectivity, routing, failover, and consistency problems, not only with these links, but also the links leading to the remote databases. So we do actually run remote databases, and I have to say it is a lot harder, about an order of magnitude harder and trickier to get it right at the scale we run. What helps us is that we don't store user data. So we store it until it is delivered, and then it gets deleted. So most of our data sets are served from RAM. And most our data access patterns modeled as key value, meaning operation on a single key. We also rely heavily on fast iteration over key space. And the fact that we run code right next to data helps a lot with dealing things like that. We also have a couple of graph databases, such as address book or group membership. And these are also modeled on top of key value, but they're a lot harder to get right because they have distributed indices and all of the associated consistency problems. Well, let's take a look at how backends with embedded databases work. So we partition the key space stored in the database or served by a particular backend into a number of partitions. We partition them deterministically. And then we spread these partitions across the nodes. We also group nodes in such a way that they form redundant replicated clusters that we call islands. For example, in this island over there, this node is primary for partition 1 and secondary for partition 2, and the one next to it, its peer, is the other way around. And looking at this picture, you may notice that there is another isolation level. Most our type of failures that we see in the system are single node failures, in which case a peer takes over the other peer's load. But sometimes the whole partition can get sick for various reasons, in which case the system would run just fine except for users who kind of got unlucky to be in that partition. So this is how an island looks inside. It has each node in the island runs a pair of API endpoints that is sitting on top of a database partition. an API endpoint is a gen server registered with a PG2 library. It comes with Erlang, and it's a remote service, global service registration library. So in this case, partition 1, this API endpoint would register as primary for partition 1, and this is a secondary as for partition 1. And this would be similar setup for partition 2. So normally, if everything is working fine, this node would be serving data and requests for partition 1, and this node would be serving for partition 2, would be active. So if this node, let's say this node goes down, then this node takes over partition 2 and starts serving requests for it. And you may notice that the databases are cross-replicated. So this standby has pretty much an up-to-date version of this one until it goes down. So when the service is restored, the replication stream reverse, and what happens upon service restoration, it's either this state gets reconciled using changes from here, or get completely reloaded from the peer. Well, let's see what this API endpoint and database look inside. So requests come from this API endpoint, which is a gen server, and then they get deterministically distributed over a set of workers, meaning that each key, for operations for a specific key, always go through the same worker. Worker procs talk locally to what we call DB frags. This is the next kind of level of fragmentation inside of the database partition. And I'll talk a little bit later about what this thing is. But one thing to point out is the number of workers and the number of DB frags are, they don't have one-to-one mapping. They scaled completely differently. For example, worker known to run application logic, and depending on the needs and characteristics of, like latency characteristics of requests, we may run more or less workers. So why we're doing all this? So we have two goals in mind. First, we want to serialize all operation on a single key so that there are no concurrent operation on the same key going into the database. That helps with consistency. And then, since we're partitioning the DB further so that workers accessing this DB fragments concurrently, basically we spread the lock load and locking across this DB frags. So if there was one DB frags, then for certain type of DB operations, everybody would be locking on that lock. And here, like, we have a whole bunch of them. And this is actually the key idea behind this whole DB setup. Essentially, what we're trying to achieve is achieving by this deterministic key to node to worker mapping is pushing locking and serialization to a higher application logic, and therefore avoiding more complicated and expensive locking primitives and locking operations. Let's finally see what the DB frag is. It is actually an ets table, which is a hash table that comes with Erlang with concurrent access. It's a really nice one. And on top of that, we have replication and persistence layers. So it looks like more like a real database. In practice, it comes down to two alternatives. For a very, very long time, we've been running Amnesia, and we still rely on Amnesia heavily in current production system. So we run it with async dirty. All the operations run with async dirty, meaning that there are no transaction, no DB level locking, but we do use disk logging for persistence and asynchronous replication. So we had to modify it pretty heavily to scale for what we're using it for, but it's still not flexible enough. So therefore forgets. So if some of you may be familiar with the history behind amnesia spelling, it was meant to be called amnesia, but it was considered inappropriate for a persistent database to be called amnesia. So we didn't shy away from picking a completely inappropriate name for a persistent database. So that's. I won't talk much about forgets. It's a wonderful new system. I'm very excited about it because it pushed our successful database model to the next level. One of our engineers, Mikhail, who is actually here, if you have any questions, is giving a talk on it later this year in Stockholm. So I mentioned just a couple of things. First of all, replication works very reliably across slow networks, long links, network disconnects, and all sorts of problems. It runs masterless with several different data reconciliation modes. So we do have inconsistencies of data in data as usually because of net splits and nodes being in an unstable configuration when one node is kind of almost crashing but not always. Thankfully, forgets can do a lot of us automatically, and sometimes this reconciliation logic can be pushed to the application level. It rebalances, when it comes to capacity scaling, it rebalances data at a dB frag level compared to Amnesia, which is, has to be rebalanced at a key level. And it also has some extra features. I'll mention just one, which is automatic automatic record expiration. To summarize the benefits of our database setup. So it's a fairly simple system, easy to reason about, has few moving pieces, and we get very predictable behavior from it, and also efficiency. So for example, read, modify, write are very tight operations, very low overhead, and key space crawls, key iteration also runs very efficiently in this embedded mode. We were able to successfully scale with this model up to this point. So it's been really, really working well for us. And one of the most interesting features is that it is not a black box. It is completely understood and run by the team who owns the backend, which means whatever changes we need to make in terms of scaling, change in data representation, data model, it all can be handled with no coordination by a single team. So, and this is how far we pushed it. So this was our biggest database that we don't run anymore because we don't need to, but that was our largest. A couple of less obvious comments on performance. So generally, so this one comes down to optimizing the number of messages, minimizing the number of messages and the number of hops. Typically, each message, although message passing is very efficient in Erlang, it still has a non-zero CPU, garbage collection, scheduling, overhead, and sometimes they have nonlinear interplay with each other. So it's just a very good idea to avoid extra hops. So this one is a pretty obvious one. So when client sends a request, it goes through an API endpoint, but the response goes back to the client directly. Another thing that we do, sometimes we Instead of going through API endpoint, we go to the worker proc directly to save one hop. That implies that these worker procs never go down. We also don't use gen server callcast remotely. It's a really, really expensive operation because under the hood it does remote monitors, which, as far as I remember, require 2 network hops. First, you need to set a monitor, then do the call, then do the demonitor, which is really, really expensive and unnecessarily so. So why is it? So we don't use monitors. What do we use instead? So in our system, we have all kind of problems, in fact, in any distributed systems, the nodes can just become slow for a lot of reasons. They may plainly crash because of a hardware problem. There could be network connectivity problems, and the request can be dropped because of overload control on the server. So for all of these cases, to account for all of these cases, we rely on timeouts. Basically, a client issues a request with a timeout. If it doesn't come back in time, it's considered unsuccessful. And then there may or may not be retry logic depending on the operation. We also try to use one-way messages when possible, just as an extra optimization. So this is another example where you can use parallelization to reduce, to make things faster and reduce contention and log contention. In my previous diagrams, the server node interaction started with the API proc, but actually before it lands in the API endpoint, it has to go through a disport, which we have many, for example, in a large, nodes in a large front-end cluster would be connected to like a single backend node. And obviously, like if all requests go through a single API proc, meaning there is a single log here, it can quickly turn into a bottleneck. Besides whatever the DQ logic and forwarding logic here is also not free. So the default solution in this case, we just parallelize by running multiple API endpoints serving different partitions. So like very easy thing, very simple, and addresses the problem. And that's one of the reasons why in practice we often run more than one key partition per node. Right, this one is a tricky one. So in my opinion, Erlang was not built for handling overload. And I'll try to explain why I think so. I have a hypothesis that it was the original use cases when Erlang was designed. In traditional telecom systems, there's basically either no overload, you have a fixed number of channels and that's it. So there is no kind of application level logic that has to deal with overload. Or it could be that it's just the system is not, like, if it's overloaded, then there is no guarantee on the service. So in our case, we have to stay up. Therefore, we have to deal with that problem and bypass some of the default Erlang mechanisms. Generally, there are two kind of ways to think about it. First of all, any type of overload manifests itself in the backlog, which in Erlang realm means queues. And the other one is obvious. It's basically we need to prevent cascading failures, prevent slowness in one place to be propagated through the system. So this is a very general statement about how we approach it. We try to remove all backpressure. Let's look at a typical cross-node request path. Client procs send a request to a remote node. It goes through the disport, comes out of the disport on the other end, gets distributed through API procs and land on the work proc. So what happens when server node becomes slow? Doesn't matter which reason. It could be it's resource, it's short on resources, it hits some concurrency limits, or there is a slow downstream system. So in that setup, the way I describe it, the first thing we'll see the process mailbox queue will grow. And many of you who have dealt with Erlang probably know what's going to happen next. So Erlang has a native backpressure mechanism, which is called sender penalty. And it's basically deprioritizes processes sending into a large queue. And this way, if we have a large queue and a worker proc, the API procs that are trying to send more requests to it will get slower, in which case it's quite possible that there will be a queue here, and finally it may spill even further. So another thing is that, well, Erlang process queues are unbounded, and we know that with the sender penalty, the system gets slower and slower as the queues are growing larger. It's actually the penalty is proportional to the size of the queue. So it is quite common failure when the node goes out of memory and crashes. And sometimes that's actually a good thing. So like if there is a problem, unaccounted problem, then it's much easier to, much better to have the node crash completely quickly, other than keeping it in a kind of half-working state, still taking requests but not doing anything. So it's easier to crash and have a clean failover than kind of struggle. So there are a couple of solutions how you can deal with it. So this was the original problem. And one of the solutions is to stick in a application level queue, basically replace the Erlang mailbox and the worker proc with a custom queue sitting in the worker pool manager. That queue would obviously, you wouldn't put any backpressure logic there. And it also can be bounded. So the problem is that it is a working model. We use it quite often, but not always. And that's because that queue is being implemented in Erlang. The queue management and garbage collection overhead associated with that is much more expensive than letting Erlang do its job. If queue sizes are not too big, obviously. So the other method is quickly discard requests when message queue exceeds certain threshold, or not in queue in the first place. This one is simple and effective. If the part of the system that you're working on is fine with bounded queue and throwing away requests. There is another variation of it, which basically says discard all old requests that are sitting in the queue. It's based on the timeout provided by the client. Usually it would be very similar to the timeout for the whole request. Right. And puts some kind of reasonable bound on how large your queue can become, unless you genuinely overload it, like you're just sending too many requests at once, in which case it wouldn't help. So this is one of the one of the greatest tools that we have in our system. Basically, most of the concurrent workloads that we run in the system is modeled in one way or another using this single module. It's called Gen Factory. So it addresses all the use cases that I talked before, plus it has many extras. For example, it has different key-to-worker mapping. It can map deterministically, or just round robin through the workers, or do the FIFO. Workers can have state, which we use for outgoing HTTP client connections, for example. It supports request pipelining, which is really helpful in some cases. And it can detect and kill workers that are stuck, that cannot go through a single request fast enough. And it's also integrated with all our operational and monitoring tools. For example, for watching queue sizes, for measuring throughput, for setting queue bounds, for flushing the queues, and so on. Right. Well, let's switch to the client. So what happens? The client nodes that's actually sent the request. So if the server node becomes slow or the network becomes slow, it puts the disport queues starts to grow. And although disport queues, unlike Erlang mailboxes are bounded, there is a mechanism in Erlang that is by default, if you do normal Erlang send, the client proc sending into a busy disport will get suspended. And what happens if that client proc is a pretty active one and other parts of the system is actively sending into it? So what will happen? Well, it's going to queue, or there could be other queues in the system because, for example, in the case of our front-end nodes, like they're both kind of client and server at the same time. It's very symmetrical. And if that happens, there is a high chance of it going out of memory or triggering a cascading failure because of that. What are the solutions for these problems? So one solution that we rely quite heavily in a normal Erlang distribution setup is we send with a no suspend option instead of a normal send. And what it does, it basically, if it sends into a busy port with that, it just discards the message. We also run dist port buffers with disports with large buffers, which help with the intermediate network problems, but does not help with disconnect. Here's another solution that we also use, and that's a pretty obvious one. Instead of like relying on queuing logic and suspension mechanism and disport, so you just stuck a queue here, a buffer, and do it in like your own code the way you want. And we often use it in front-end nodes for outbound queues for each of the destination nodes. Here's another solution. So it's called wandist. The primary use case for wandist, I'm going to mention it later, is this is something that we use for connecting dist clusters with each other. But it has some nice properties. It transparently handles TCP reconnect, unlike dist. Dist kind of disconnects, and then it could block the whole system trying to reconnect. It provides reliable delivery. It can detect black-holed TCP connections, and because of that, it kind of has to have to do buffering, which is essentially what this custom thing does, but does it by default. Generally, there are several different types of queues in Erlang. We already mentioned port queues and process queues. In R20, there is a off-heap parameter that basically removes the garbage collection overhead from if your process runs with a large queue, at least it won't be garbage collected. You can do custom queues, and we do them using lists or at tables. There is a natural Erlang process queue, which is basically spawning in process and then waiting until it finishes what it's supposed to be doing. And you can use any combination of the above to model what you want. Erlang kind of makes it easy to reason about it. None of it is like very well understood and documented. But once you understand it, it's not too bad. It's possible to handle it. But that's one of the reasons why I'm giving this talk, is just to show you like some of the non-trivial bits of Erlang behavior. So, and just to iterate, backlog is by far the most important operational metric in our system. So usually when the system starts struggling or having problems, any kinds of problems, it manifests itself as a backlog. To sum it up, this is kind of the framework how we approach concurrency. In backend, in fact, pretty much all of the use cases go through GenFactory, which is a worker pool with various configuration depending on what the backend does. Sometimes we run it with just a handful of workers to parallelize across the available CPU cores, or with many more workers if we're going to external resources and have some either long latencies or uneven latency distribution. And Erlang works really, really well with that. And one important thing is that for backend, our concurrency is always bounded, which is maybe a little unconventional for Erlang systems, but it makes it easier to reason about, and also easier to surface all the kind of operational stuff, especially when it comes to firefighting, dealing with problems, and observing the system behavior. So on the front end, there is a natural concurrency because we run a process for each active connection, active session. So at peak, we run about 500,000 concurrent processes each handling a TCP connection at the same time on a single node. And we also heavily rely, again, on GenFactory for chat-to-chat communication. We rarely use spawn directly, but good thing it's always there, so we can use it whenever we feel like it. Right, so a couple of things about how we run large Erlang clusters. So we still rely on this because it's very efficient and has been working for us very well. This is one of our larger clusters. So as you can see, it has over 1,000 nodes. And all of the dist problems are pretty much known at this point. It requires a lot of connections because it has a full mesh connectivity, maintains. And it's also not flexible enough, as I explained in some of the earlier slides. So therefore, we created wandist. So wandist connects only clusters that need to talk to each other. Like if we have cluster A and B, and all nodes in cluster A would be connected with all nodes in cluster B. So it's kind of a partial mesh. Another thing that it does, it publishes PG2 groups across clusters. It transparently handles slow network reconnects and keeps nodes always connected, and also does reliable delivery, provided that the nodes don't stay disconnected for a long time, in which case we hit the buffer bounds and we'll start dropping messages. We have a need for some custom authentication and encryption, which we do that in wandist. And it is all implemented in plain Erlang on top of GenTCP, which means it is more resource intensive to run things over wandist. And that's one of the reasons why we still use dist. So a couple of, well, actually more than a couple of things on how we run the system. These are our two most common problems: seek or crash node due to hardware problem or bad code push. So as I mentioned earlier, like the best way to deal with it is have it crash quickly or stop it explicitly, let it fail over, and then deal with whatever problem is on that node. And the other one, which is much less obvious how to deal with it, is the backlog. And the main goal is to here all the effort is directed to prevent propagating slowness and failures through the cluster because of one backlog in one place. We've seen some bad outages where we had to fully gate the system, drain the load completely, just to allow the system to recover. So, like, it's basically the crux of it. To keep the system running, you need to figure out how to do failure isolation. Therefore comes monitoring. So if backlog is the most important thing, so how we go about it? So first of all, we get alerted when the queues grow large. For example, if the node has been running with relatively large queues for some time, when worker queue in a single worker exceeds certain threshold, or when a bounded queue starts discarding requests. So once we discover that, what do we do? Where do we look? We kind of need to figure out what's going on, how bad is the problem, and the other part, like why is it happening and where exactly it's happening. So typically, the first step to answer the question how bad it is and where it's happening, we pull beam stats at a second-by-second resolution and get the aggregate total of all queues and some extra information that allows us to reason what's going on, like why is this thing happening. And sometimes we do have to look at a lot of more granular stats that are also exposed as by Beam. So one thing to think about it is Erlang VM is a complicated thing. It is quite comparable to like operating system like Linux. So if you're running system at a high load at such scale, you'd have to invest time and try to understand what's going on. Well, you can learn it as you go, of course, but just to set some expectations, what you might have to deal with. So once we kind of know what's roughly going on, we can go granular and see some of the things about the specific queues build up. So for that, we log for each process that has a non-zero queue information about it, like what kind of process is it, and how bad is the problem, whether it keeps queuing or it's actually draining, for example. And then some of the extra information to get us an insight about why it's happening. And oftentimes we would use that for forensic analysis, like a node crashes, then we go there and see what exactly went wrong. Deploys. Well, I'm proud to say that we do love hot code loading. We use it heavily. And we've been doing that historically, and there are a couple of good reasons why we've been doing it. So one is we run a large number of runtime servers, each handling a active session. So if we can hot load so that the user session do not get disconnected, disrupted, and they just continue as normal, which is a huge benefit for us. And another one is embedded backends. So backends operations are, well, not easy in any case. So like by not restarting embedded databases, we avoid just the time it takes to reconcile, to reload the state, and things like that. And the system is kind of less shaky because of that. And as a result, we can roll out changes even for large clusters within minutes, which is a big part of how we approach things. Well, of course, it doesn't come always easy, so we have to be mindful about load order for individual modules, the state migration, records. I don't have a solution for records. Good solution. If you know one, please let me know. But we got the state migration for gen servers and things like that pretty streamlined. It's actually pretty easy for us. Beam patches. So I'm happy to say that Beam is getting better with each release. We used to do a lot of patching in R16, but now everything that I described you can achieve with pretty much vanilla Erlang R20. The only exceptions would be Amnesia and PG2, which we heavily modify to allow us to scale. But everything else is minor performance optimizations, monitoring, and things like that. So it was much more prominent on R16. This is the last slide. So Erlang gives us some tremendous advantages. It would be A very, very long list. I actually started writing it, but I gave up. We do what we do, and I've been able to scale, support all the products features, keep a very high standard for availability. And what's dear to me is we're still very, very efficient as engineers. Very, very low overhead dealing with the system. With that, thank you so much for listening. Yeah, and if any of that sounds interesting to you, if you're interested in those type of things, I encourage you to talk to us. There is a number of us server engineers here in the room and around in the conference. So yeah, I would be happy to answer any questions.
We have time for a couple of questions.
So you said you were relying on timeouts everywhere, so using a lot of timeouts, I can understand.
Yep.
Had problems with timing wheels way back. So are you using Erlang timeouts, or are you using your own time to live? And you were also saying you're using one-way messages as much as possible, so I guess.
Well, it's not always to use one-way messages because it's kind of like, it depends on the nature of data, right? So if you can kind of live with some temporary inconsistency, that's fine. But to answer your question, I know that we had some performance patches in TimerWell, but that was in Erlang R16. I don't think we do it anymore in Erlang 20. The system has been heavily reworked for performance recently. So I'll defer to my colleague who's probably more knowledgeable in that. So if you could stay after the talk, we can discuss that.
All right, so I think that's all the time we have. So I'm sure Anton will be happy to
Yep.
answer any questions later today.
All right, thank you.